Hello, my name is Louisa Adwoa Koranteng from the Data Science and Analytics morning session. Today, I'm going to be talking about the cache memory and its mapping techniques. Before we begin, let's discuss what a cache memory is. So, a cache memory is a small, fast memory component that stores frequently accessed data, significantly speeding up CPU operations by reducing the need to access slower main memory. However, because it is limited in size, we need smart strategies to decide what goes into the cache, and this is where memory mapping comes in. Memory mapping. Memory mapping defines how data blocks from the main memory are placed into the cache memory. This strategy is crucial because it determines where specific data can reside within the cache, directly impacting performance and efficiency. The primary role is to establish a connection or a set of rules for translating main memory addresses to cache memory addresses. This ensures that when the CPU requests data, the cache controller knows exactly where to look for it in the high-speed cache or if it needs to fetch it from the slower main memory. And there are several types of memory mapping techniques. And today we are going to be talking about three. We have the direct mapping, fully associative mapping, and the set associative mapping. Direct mapping. In direct mapping, each block from the main memory has one and only one possible location in the cache. For example, main memory blocks 0, 16, and 32 might all map to cache line 0. This simplicity comes from a straightforward address decomposition. So the memory address is divided into three parts, which is the tag bits that is used to identify the specific block, index bits used to determine the cache line, and the offset bits to pinpoint the word within the block. An advantage of using the direct mapping is it is a simple hardware implementation and very fast lookup times, as only one comparison is needed to check for a cache hit. Disadvantage: the main drawback is a high potential for conflict misses. If multiple frequently used blocks happen to map to the same cache line, they will constantly evict each other, leading to poor performance. Next is the fully associative mapping. Fully associative mapping offers the most flexible, allowing any main memory block to be stored in any available cache line. This approach maximizes cache utilization, but at a significant hardware cost. Advantage of using the fully associative mapping is the method yields the highest hit rate amongst all the mapping techniques because it virtually eliminates conflict misses. It provides the most flexible data placement, ensuring that a block remains in cache as long as there's space. Disadvantage: the need for a comparator circuit for every cache line makes the hardware highly complex and expensive, especially for the larger caches. This parallel search also leads to slower lookup times compared to the direct mapping, as all comparisons must complete before a hit can be determined. And lastly, we are going to be looking at the set associative mapping. The set associative mapping combines aspects of both direct and the fully associative mapping. Main memory blocks are grouped into sets within the cache. A block can be placed into any line within its designated set. Address split. The memory address is divided into three parts: the tag bit, set, and index. bits. An example, if a cache has 16 lines and is a two-way set associative, it has 8 sets, which is 16 lines divided by 2 lines per set. Main memory blocks map to a specific set based on their memory address. Once in a set, a block can occupy any of the 2 lines within that set. Advantage: this approach reduces conflict misses compared to direct mapping, as multiple blocks can reside within the same set. It offers a good balance between hit rate and hardware cost, requiring fewer comparators than fully associative mapping while still providing flexibility. Lookup times are faster than fully associative but slower than direct mapping. Disadvantage: it is more complex to implement than direct mapping due to the need for multiple comparators per set and a replacement policy like the LRU to decide which block to evict when a set is full. Next, we are going to be talking about the replacement policies. So there are a few types of replacement policies, but we are going to be talking about the round robin, which is the common algorithm used in caches to decide which block to evict when a new block needs to be brought in. It operates on a fair principle, ensuring no block is neglected. The round-robin policy evicts the block that has been in the cache the longest since its last access, cycling through the cache lines. Advantage: round robin is simple to implement and ensures fairness by cycling through cache lines. Disadvantage: round robin doesn't consider block usage, so frequently used blocks could be evicted, leading to lower hit rates than policies like LRU. Importance of cache mapping and replacement policies. Why we do cache mapping? So, one, to optimize performance. Crucial for maximizing CPU speed by ensuring rapid data access and minimizing main memory lookup. Secondly, design trade-offs. It balances hardware complexity, cost, and performance, influencing system architecture and economic viability. Thirdly, efficient resource use. It is vital for effective cache utilization, ensuring critical and frequently used data remains available. Fourth, minimize latency. Strategic data management reduces memory access latency, preventing bottlenecks and improving system responsiveness. This brings us to the end of our discussion on cache mapping and its techniques, and also some replacement policies. Thank you very much. What do you mean Zoom quit? So all this time it wasn't recording. You've got to be fucked.